Hello world, this is Craig. This is the little perf board that I populated with a 2732 EPROM and a little address decoder so that I could hang that on the MIL mod system. I wanted this when I was putting the system together and porting code over. It's just a lot easier to use the 2732 than it is to populate and program all of the 1702A EPROMs. So I wanted to make a finished version of this board. And so before Christmas, I went ahead and designed a system and laid it out, sent it off to one of the board houses, and these came back on New Year's Eve. So a couple of days ago, I was able to populate it and get it going. So let's look at what we have on the board. This is basically the EPROM and the ZIF socket for the 2732 to replace the original board that I made. But I decided to add two more EPROMs, one in 2716 and one more 2732. This 2716 is a 2K, so that one can completely replace the MOD4 ROM board, and this 2732 is a 4K, so that could replace the two ROM boards for the 8080 monitor. I also wanted the memory address mapping for these three EPROMs to be individually addressable, so I put in little diff switches for each one and address decoders so we can individually decide where each of these are. So for example, this one could be the monitor 8, this one could be the monitor 80, and then this can be some code that's under development, or confidence tester or whatever you have. In order to be able to swap these in and out easily, I also put on some enable-disable switches on the side. So we have enable-disable switches for all three of the EPROMs, one for the 2K base, then one for the one that's in the ZIF socket, and one that's for the other one that's in the socket. So with this part of the circuit down here, this is the address set for each of the EPROMs, and then these switches down here, this one, and that one are the enable-disable switches for each of the EPROMs. The next thing I wanted to have on this board was a bus output. So you can see I have LEDs across the top. We have our data bus here. This is all of our address bus. If it's the 8008, these are our flags. And then this is the bus signals and some other miscellaneous LEDs up here at the top. While I was doing all of that, I decided to go ahead and put a single step capabilities on this board. So we have a switch right here. It's a 3-position switch. If this is in the up position, it is in a normal run mode. So we can put it in the up position, start the program, and we can see that we have our data up here. Most of these, they just look like they're completely lit because the program's just going at full speed. And this is just a program that is sending pulsing this little speaker. I do have a 4-bit port that I put on this for another reason I'll tell you in a bit. And so since I had that 4-bit port, I decided to go ahead and hang a speaker on this so it can make some noise. All the LEDs look like they're on. You can see with this program, which is just doing a little sawtooth wave ramp, these two LEDs, the latches right now. So let me back up a bit. All of these LEDs have drivers that are also latches. So we have driver latches on these. They're operating right now in a transparent mode so that whatever is on the input is just coming out to the output. But we're also loading some variables, moving some data around. We're seeing these vary in intensity depending on the frequency of us visiting that memory address. This is what we see when we have all of these latches in transparent mode, so we constantly see it, but I do have jumpers here. I put some 1 of 4 jumpers on this that control these latches so we can decide exactly what latches this output if we're looking for a specific thing. With this switch in the center position, we're in single step mode. We have a little LED here that tells us every time that we've completed that single step, and we have the button here that gives us a single step. So we can watch our addresses. Right now we're at address 0, and we have in here a 3-1 in address 0, which is the LXI stack pointer instruction. We push the single step button. We're now on address 1, and we have a 1-4, which is where we're putting our stack pointer. Push our button again. We're at address 3, and we have a 2-1. We're going to load a value into the counter. Here, the next instruction, we have a FF. This is the value that we're loading. So you can see that we can go through and push this, and every time we push it, it takes us to the next instruction. Now, sometimes we're at certain portions of the code where we don't want to just single step it. It's convenient to have what I'm calling the slow step. That is, we can put the switch in the bottom position, and when we do this, I have a little 555 timer on here that is pushing the single step button for us. We can see that it's just going through the code, and it's single stepping. You can see the little single step LED right here flashing every time that it goes through a single step. And because we sometimes want to change how fast it does that, we have a little 4-turn pot here. We can slow it down. So we can slow it down to about 3/4 of a hertz, or we can speed it up. And we can take it up to, I'm not sure, maybe 60 hertz or so. One of the things I wanted to do with this ability to do the slow step and the single step is I added this 4-bit port that I mentioned. 2 of them just come out to LEDs, 1 of them runs the speaker, and 1 of them runs a single step override. So what we can do is in the code we can write out to that port when we want it to enter the single step mode. So we can have a bunch of code and we put our switch down into the single step position, but we write a single step override out to this port. The code will run in real time, and then when we are to the portion of the code that we want a single step, we would put in an out instruction that would then enable the single step, and it would go into the single step mode. Then after we're through with the single step mode, we could either, by another out instruction in the code, we could take it out of single step mode, or we could flip the switch up, take it out of single step mode. Another thing that I added to this, oh, by the way, that port, so I have jumpers over here where we can set that port address. Independent of all the other addresses. I also brought out just the addresses and a couple of grounds here for logic analyzer when you're doing something that it's convenient to have the logic analyzer. That's this board in a nutshell. There are a couple of limitations. One limitation is that we don't have the sync signal coming out onto the bus on the MIL mod system, so we can't do a true instruction single step. With the sync signal, we would know that every time we saw the sync signal, we have completed an instruction, because that toggles at the beginning of every machine instruction. So without the sync signal, what I used on this board was the memory read. So when we're doing the single step, we're actually jumping from memory read to memory read, which isn't always the same as from instruction to instruction. When you're doing the single step, then you will notice that this doesn't single step individual machine instructions, it single steps by address. The other little limitation on this is when they laid out the processor boards for the MIL MOD8, they just brought the ready signal in unsynchronized. If you look at the spec sheet, you can see that the ready signal has to be stable with respect to Phi 2, the falling edge of Phi 2. There's a minimum setup time. On both of the CPU boards, they just brought the ready signal right off of the bus into the processor, and they didn't do any synchronization of this with the clock. So to make this board run properly in single step mode, what we have to do is I've added a little flip-flop to the Phi 1, because there is a TTL version of the Phi 1 available on the processor board. So I have a flip-flop that basically takes the ready as the D input. It waits until the edge of the Phi 2 clock, and then it will clock that out into the processor. This is the input to the flip-flop, so this is essentially the ready coming from the single step board. This is the Phi 1 TTL clock on the processor board, and this is the output of the flip-flop. So here is one instruction that we allowed it to go, and then we took the ready low and told it not to do any more instructions, and then the ready pops high for a second and lets it do the next instruction. If we zoom in on one of these areas, we can see where the ready goes high. And what happens is if you let the ready go high at any arbitrary time, and in this case, it's probably a good example that this is Phi 1, so that means that Phi 2 went low right before that, and we can see that we possibly would have taken the ready high right in the middle of a transition of phi 2. And what will happen is it'll work for a while. The single step will work just fine. If you happen to take ready high when you are right before this little TRS or this T hold time, when phi 2 is about to do a transition and you take the ready high, that'll lock the system up. And it'll work fine, 50, 100, a few hundred single steps, but eventually it will lock the system up. So I put in this little D flip-flop. What happens is we can see that this is our input, so it let the ready go high, but rather than give it to the processor, this is the output right here, rather than give it to the processor right away, it waited until this rising edge transition of the phi 2. So that gave us our proper synchronization going into the processor. If we didn't do this, we don't do this little patch on the processor board. We have to do this for both the 8080 and the 8008. If we don't do that little patch, the single step will go for some period of time and then it'll eventually lock up. During this period of time, there's four clock pulses here where it's doing that instruction. The ready went low and the flip-flop sends it out to the processor. Now we don't have to synchronize the high to low transition. We can set the ready low anytime we want, but we do have to synchronize that low to high transition. So that's one limitation on this board, is we do have to modify the processor board if we want to use the single step. Well, that's the board in a nutshell, and you can see it's has its handy things. The size-wise, it is designed just so that the ZIF and the single step components stick out a little bit further than an average board so that you can access them. There are some patches I had to make on this and some changes that I would do on a next version. I'm not sure if I'm going to do another revision or not. It depends on if anybody's interested in getting some of these boards. But if I do another revision, there's some things that I would change. First of all, these switches really bug me. I got the single step switch right, but I thought I triple checked these, but all these switches I have in backwards, and so they're upside down. So when they're down, it enables, and when they're up, it disables that EPROM. So those switches bug me a lot. The other thing is this is a 518. These are our comparators for our addresses to enable the EPROMs and our port. For the EPROMs, this is a 521. For the port, it's a 518. The difference being that the 518 is high when the values are equal, and also it's open collector, which didn't matter for this. But I wanted the high for the latch on the port, and I had a 518. I thought everything was good, but then I put this together. My 518s were dead. I looked at buying a 518 from DigiKey, and they're $10, so I'm not paying highway robbery prices for a 518. So I rewired this, put in a 521, and I used a leftover inverter on my gate that I wasn't using. So I'd also just switch that out for the 521 rather than the 518. I'm not sure how it happened, but the two latches, these two, my library had the power rails backwards on those, or maybe I just missed it somehow and connected them backwards. But at any rate, these two I had to patch the power rails on those. I need to fix those also. And let's see, so I had these patches on the back. I think that was it. There were the ones for the power rail. There was the one to put the inverter in place of the 518. And I think those were all the patches I had to make on this. So I haven't decided if I'm going to make another board or just live with these patches. By the time, it's going to be a lot of work to depopulate this, and certainly there's a lot invested in the LEDs and everything, and I don't want to throw it away. So we'll just see what happens. But I'm going to go ahead and update the schematic for a version 2 or version 1.1 that has these corrections, so that when we do patch it, we remember what we did. That's it for this board. I wanted to introduce it, see if anybody has an interest in it, and some of the things like the single step, we might go into a little bit of more detail later of how I did the single step circuit. But if you want the schematics, I can send you a copy of the schematics so you can see exactly what I'm doing on this. All right, well, I hope you got something out of that, and that's my contribution to the MOD8 system. I named this the MOD8-20 for no good reason other than this 2020. And I thought I'd take if I make any boards for this system, I thought I'd take the 20 and the 20 to 29 bracket. Okay, if you have any questions, let me know, but I appreciate you watching the video, and I will talk with you later. Thanks, bye.